Thanks, Simon, and also welcome from my side to our webinar, Troubleshooting in Food Packaging Materials by FTI Microscopy. Food packaging materials is really an interesting product as everybody has to deal with, especially when we go grocery shopping in the supermarket. Because most of the products there are wrapped or packed in plastic or multi-layer foils. That means it is really interfering most of our life, and especially these kind of products are really high-tech materials because there are so many layers, including such a multi-layer foil, which is just being used for candy bars or sausages packaging materials. That's really interesting, and therefore it is worth to keep an eye on it, especially with FTI microscopy we want to use, especially today. Today we just have prepared some examples for you. One of these is such a kind of multi-layer foil which should show an oxygen barrier, and there it is important if this barrier is present, especially which has been used, that these kind of products which are packed in there stay longer time fresh in the supermarket. And the second sample is a cold seal candy wrapper. So that means the process how the cold seal is being applied on the wrapping material itself could cause some troubles to the foil itself, and therefore it's also worth to keep an eye on it and to analyze it by FTI microscopy. But before we do so, we want to bring everyone here at the same page, which means we just want to repeat the fundamental basics for FTI spectroscopy and ATR and microscopy itself. So therefore, I just want to show you some kind of these basics. So the principles of infrared spectroscopy are as follows. For this technique, we make use of IR radiation, which is generated by a light source, and this light has been directed at a sample. The sample is reflecting a part of the light, but also the sample absorbs a very specific amount of the passing light. And the remaining light, which is transmitted and collected by a detector, is then creating our IR spectrum of a very specific signature of the sample we have analyzed. For food packaging materials, but also for many other polymer applications, we cannot make use of transmittance or reflection mode as the sample is neither transparent nor reflectance. So that means we should make use of another technique, and this technique is called attenuate total reflection, or in short, ATR. With this technique, we do not need a reflective or transmittive properties of the samples, which means the sample can be really opaque or intransparent, or even black polymer can be analyzed with this kind of measurement technique. And how this technique will work, this is I want to show you right now. Also here, we need an IR source, a detector, and an ATR crystal, which is usually being made of zinc selenide, diamond, or germanium. The ATR crystal must have a higher refractive index than the sample which should be investigated. The sample is placed on the ATR crystal, and the good contact between the crystal and the sample is very important. And in this case, for spectroscopy or the IR microscopy, we make use of specific tools to guarantee a good contact between sample and crystal itself. So the IR light is then passing the crystal, which is reflected internally and is partially absorbed by the sample on top. Due to these wave-like properties, the IR light slightly penetrates into the optically less dense sample. Within this so-called evanescent field, the IR light interacts with the sample, and the intensity of the evanescent field decays exponentially, and the light only interacts with the very first few microns. The reflected light now carries the information, the absorbed information of the sample, and is collected at a detector, which is then providing the IR spectrum of the sample, which is also very unique. The system we want to use here is the FTI microscope Lumos 2. This system is a fully automated system and really perfect for the use of this kind of food packaging materials. So the system provides fully automated system. So there we also have an ATR crystal with this integrated pressure sensor, which is exactly this tool what I mentioned before that guarantees a perfect contact between the sample and the crystal so that the ATR crystal could be realized. Also important is for the system is to have a large working distance and a very large maximum sample height so that even bulky or very structured samples or high-res samples could be easily analyzed on deep-seated positions, like you can see it here on this picture. We can carry up to 3 detectors, especially this FPA imaging detector I want to make you aware of, because this is the detector we want to make use for our sample measurements right afterwards. Because with this detector, we can really achieve high spatial resolution and highest scan rates of certain large areas. So what you see here on the right-hand side is the live measurement of this FPA detector, which is acting like a digital camera in the infrared range. That means each pixel provides a complete infrared spectrum, which is also spatially resolved. And due to the fact that we do not need any apertures, we can really achieve much more higher spatial resolutions than with single element detectors. So each tile, what you see here, is providing more than 1,000 spatially resolved spectra with one measurement spot. And therefore, in this case, we can really achieve more than 900 spectra per second, which are laterally resolved. Also, we can provide a low cost of ownership. So that means with long-term warranties with the system, it makes it really a working horse in this kind of application. So, but now we really want to start with the measurement itself. So the first sample we want to analyze is a food packaging sample which contains a certain kind of oxygen barrier. These kind of oxygen barriers are used for fresh food which has been packed in this foils in order to keep them more a longer time fresh in the supermarket. So, and especially this kind of oxygen barrier, which we can use for this food packaging material, we have used here in this foil, which is being done the raw material before it is being packed and printed like this we have seen right now. And in this case, there's a very small EVOH oxygen barrier included, which should be 1.8 micrometer. And this is exactly what we want to resolve and to check if this has been homogeneous and present all over the sample. And therefore, we want to measure this kind of specimen. But before we do so, we need a certain kind of preparation of this sample because it's a multi-layer sample. We cannot just measure through it. So because we want to measure it with ATR, so in this case, we really want to distinguish all the layers, and especially therefore, we need to fix it in an upright position. And how to do this and how this complete procedure will be done. Therefore, I have prepared a small video which I really want to show you right now. So here I've prepared the video. So that means in order to prepare this kind of sample, we make use of this microvise holder, which has 2 metal brackets on the side. We make use of a tweezer. This is the sample, so it's a small cutout of the sample. We make use of 2 PTFE foils, which will be used as a buffer material to protect it at the side of the metal brackets. So we put the sample in between these 2 PTFE brackets, attach it to the microvise holder, make sure that the sample will stick out, and then we cut it with a micron blade or with a scalpel in one steady cut, and then we can see the strips in here, and then we have a very smooth cut of the surface of our sample, which can then be used in a microscope for the analysis. And that's the result. So this is exactly the sample like we have seen in the video. we have this microVice holder, the two metal brackets in here, and in between we have the PTFE bracket, our sample with the EVOH oxygen barrier, and also then on the side the second PTFE bracket. And exactly this sample we will now bring in our microscope. Therefore, I zoom in to the sample stage. So this is the flat and even sample stage where we can now put in these kind of sample. It's shiny, like so. Now you can see it. So that means we have the objective on the top side. We have the stage here, and now we bring in this accessory in here and have it in our fixed in our beam path then here. So then we go to our microscope. In this case, switch on the light, and now we have to make use of the joystick to focus on our surface. So what you can see here is on the one hand side, here on the left, these are the metal brackets from the microVice holder. The same on the right side. You see here this bright grayish layer here on left and here on right. This is the PTFE buffer material, and only this thing in this foil in the center, this is our sample itself, our packaging material, which should now be analyzed by FTI ATI imaging microscopy. So before we start, let's just focus a bit more on the surface, what we can use here also to activate a zoom in order to get a more appropriate image. So and then we just make use, and we can see that there's a layer on the left, there's a layer on the right, and in between there is something else. So, but in the visual contrast, it's hard to distinguish, but in IR we will see. So the complete workflow is as follows: that we have this wizard guided measurement. So the wizard itself is just providing us these kind of functions which are relevant for the current step of the analysis. In this case, it is to collect visual images. So everything what is here is to collect visual images. So in this case, we do so, collect single image. Image will be collected and provided on the right-hand side. Afterwards, we can just go ahead. And next step would be to select the detectors. So in this case, you see that we can have more than, or we have here these 3 detectors which are inside the microscope. We have a thermoelectrical cooled MCT detector, which is able to be used without the presence of liquid nitrogen for sensitive measurements in the IR. We have a liquid nitrogen cooled version of this detector for even higher sensitivity, and for highest spatial resolution, this focal plane array detector with 32 by 32 pixels. And this is what we want to use. So, and now we have to make a decision what kind of measurement mode we want to acquire. In this case, as mentioned, we make use of the attenuated total reflection, which is then the ATR mode. We make use of an automatic background, and then we have our scan time, which is 10 scans. We have a position speed with the pressure sensor, so we can define how much pressure you want to apply onto the sample between crystal and sample. Medium is, for most of the applications, really sufficient, and then we just define the area we want to measure. So then we just define here an area, something like this, and here we get an additional combo box. We then provided that in X direction, we have 3 tiles, so 3 FPA measurement positions, and in Y direction, only 1. If we confirm like this, then we will have this area. We can also move around. And what we can do is that in this area, we have defined not just 3 measurement spots. So in total, we are talking here about more than 3,000 spectra, which are collected in a spatially resolved way. So, and then we just continue. We give this sample a certain naming, let's say oxygen barrier foil. We can say where we want to store it, and then we start the measurement. So now you see that the stage is now moving downwards to give space for the ATR crystal, which is located inside the objective and is now going outside and into the focus position in order to acquire the background for FPA ATR imaging. So this is now taking place right now. So the scans are acquired right now. And when the background measurement had been finished, the crystal will move into its focus position and its in its pressure settings for the pressure between crystal and sample, and the stage has been raised and gets in touch with the sample. The stage stops immediately when the pressure is being reached with the which we have pre-selected, and now the very first measurement spot is being now collected, and we should now get the previous spectrum after the first tile, after the first 1000 spectra right now. So we see that we have here this first layer in here. We see that we have here this surrounding material of this PE layer. As soon as the second measurement spot had been finished, we will get the next one as well. And then we will get the third one. So you see that now here we get immediately the visual in the IR image, which is really matching in this case. And then we also will get now, after the third measurement position, the complete FPA imaging has been finished. Afterwards, the crystal will move back to its housing to make the beam path free for another visual image after the measurement. So therefore, we can focus back on the sample. So then we see here the imprints of the crystal, which is totally normal. This is also an indication that we have a good contact between crystal and sample. And then we can create another image after the measurement. And then we proceed with next. So and then we get this overview. So in this case, I can also show you, for example, the complete sample. Just make this field of view a bit larger. So we have here this sample. We have here the blue position, the blue spectrum, or the red position. I just skip this because then we can also make use to make here the black one for this PE layer. And in between, there's also something less. So in this case, we can also make select the spectrum, change the color maybe to red. And then we, in order to check if this layer here in between is really the EVOH layer, what we are looking for, therefore we should integrate the substance-specific bands for EVOH, which would be the OH vibration bands, which is here between 3500 and 3100 are located. Integrate those, and then we should get here this layer. We can also now select this upper and lower limits for our trace, and the contour levels we can increase, and then we get here this pixel plot of this measurement, and we can also switch to our contour plot, and we see here really a very thin layer. How thin it is really in reality, we can now see when we zoom in, for example. So therefore, we just hide the measurement points. And what we can see here as well, we also get rid of the FPA tiles, what we see that this line is homogeneous. So there's no let's say cut in between. So that means for this area, what we have observed, it is really present. And if we now zoom in, for example, in this area, we get also then the possibility to measure the distance to see, okay, from here to here. So, and then we see, yes, this area is really something what we're talking about. So in this case, 2.5 micrometers. So this is really the estimation fits quite well. So this is really a proof for the EVOH layer, but also a proof that such small and tiny samples can really be analyzed by ATR imaging in combination with this F focal plane array imaging detector. So the second example I want to show you is such kind of chocolate bar wrapping. This wrapper is being cold sealed on both sides, so on the right side and on the left side, and also if you look on the back, also here on the back side as well. So it's cold sealed because it's not hot sealed because of the chocolate bar, the product itself, otherwise it would be melt and therefore being destroyed. And this process of applying the cold seal is a rolling process on such a plain foil. So you see, this is the plain foil, how it's been coming from the production. We have this outer side where the brand is been and everything like that, the information has been printed on. And on the back side, we have this shiny polymeric side where we which gets in contact with the product itself. So if we look more carefully on the inner side, so therefore I just zoom into the sample stage, I think then can you see it in a much more better way. So we see the shiny part is the polymeric side. And what you can see here is that, for example, a more darker area has been applied here, here, and on the side here. This is the cold seal adhesive, which has been applied by the rolling process. And this is being used to cause this causes serious damages, for example, to the polymeric foil itself. And therefore, one way to check if the damages would be there or not and how serious these damages are, one way is, of course, FTIR microscopy. And in order to check this, so therefore we have this sample holder, like this one. Therefore, we can just apply in here, put it in a stage plate. So we see now we have here a very nice area where we now can exactly measure here in the side the ATR mapping of a certain area and to see where certain damages are located or not. So to check this, we expect 3 different components within a certain measurement area. Component 1 would be the cold seal itself, which is on top of component number 2, the foil's inner layer. So these two we expect, of course, and the third one would be then a possible damage which had been caused by the production of applying the cold seal itself. So what we do is we just remove the stage plate here, and maybe just show it to you here as well in the magnified view. And then we put here this area where we measure exactly here within the circle to see where this contamination is been located, and then of course we can also identify it. So then we can also just put this one in here and check it, and then we would be ready for the analysis. The analysis itself is exactly the same way like we have done in the very first measurement. So therefore, I want to skip this part and I want to keep focused on analyzing such kind of measurement results. And this is what we want to show you here in Opus, our software itself here. So therefore, we now open here the results of the cold seal. So what you see here is the measurement area, what you have been applied. So these are 40 by 30 ATR measurement spots. That means each red square indicates one ATR measurement spot and therefore also one IR spectrum. So this measurement area has been applied over the interface between, on the whitish ground, the foil's inner face, and in more grayish colors here, the cold seal adhesive. So if we having seen here on the magnified view on the top here and also on positions there, this is the foil's inner face, and on the grayish here, this is the cold seal adhesive. So we can now having a look on the spectra, which means, okay, we have a spectrum here, maybe a spectrum there. Make this one the color in blue, and this one maybe change the color in green. So we see blue spectrum derives from cold seal, green spectrum derives from the foil's inner layer. This is what we expected. So we see chemical differences, of course, but this is not what we are really interested in. What we are really interested in is possible damage. And now it becomes pretty tricky because if we can do to having a look on each individual spectrum, this would be more than 1000 spectrum in this case, in order to see if there are chemical differences to the one what we already know. This is definitely not a very smart way of evaluation. Even smarter way would be to have an algorithm which is automatically evaluating where and how many different chemical substances are distributed and located within our measurement area. And this algorithm is the so-called adaptive k-means clustering function. This is a brand new function, and this function enables us to check in an automated way how many number of clusters, in other way, chemical substances are located within our area. For this particular example, it's not that relevant because we are expecting 3 of those. So we're expecting, as mentioned, the cold seal adhesive, the polymeric inner foil, and the third one, of course, the possible damage. And therefore, we just go ahead doing execute, and what we get is now a cluster map where we see exactly in green, we see the distribution of the foil. In blue, we see the distribution of the cold seal, and in red, in red now is pretty interesting to see this is the distribution of the possible damage maybe. So therefore we're having a look, click on a certain red part in here, and we see really it is a chemical different substance in here. So this is really the way how the algorithm is really evaluating in a very quick manner chemical differences within a huge mapping grid. And now we see, okay, it's something different. It is nothing comparable to the polymeric foil. It is nothing comparable to the foils, to the cold seal. It seems to be something a third. And now it would be, of course, beneficial to check what it is. So therefore, we just click on the red spectrum and we do a search, standard search, and we see what we get is obviously now a cellulose-based material. Oh, sorry. What we get is cellulose-based material. So blue is the best hit from the library. Red is the measured spectrum. Of course, these are real spectra and real examples from from the field, from industry. So therefore, we would not get here polished spectra. So this is something. This is a real life scenario. So therefore, the hit quality is maybe not as high than with polished spectra or demo samples, whatever. But in this case, we see a very good match. Of the blue and the blue library hit and the red measured spectrum. Of course, we see also some bands which couldn't be explained by the library spectra, but these are parts, especially here this band between 9 and 800 wave numbers, or here around 1750, but these are remainings of the cold seal. If we check, can now go ahead, oops, sorry, like this, we see this is exactly matching the cold seal, or here, the cold seal here, so that means it's a mixed spectrum of cold seal and definitely the cellulose-based material, so viscose, for example, which could be proven by the customer that this is the hidden layer underneath the inner face, which has been put a hole inside our measurement area. So this is an example how we can evaluate in a very quick and reliable manner surfaces where a certain contamination could not be seen in the visual, but be easily detected in the IR in a very smart and automated way with this smart adaptive k-means clustering method. Of course, we have also other examples in the field of food packaging material, which I want also to show you right away as well. So further examples for food packaging material characterization and troubleshooting would be, for example, analysis of oxygen barrier layers and quality control of cold seal compounds. These are exactly these examples what I've shown you before, but also root cause of packaging foil delamination, determination of multilayer inclusions, homogeneity check of coated foils, and also the characterization of multilayer systems itself. So start with the root cause of packaging foil delamination. So delamination could be caused by insufficient melting processes, which could cause gel bubbles, air inclusions between layers, and also, of course, foreign contaminations deriving during the manufacturing process. In our example, what we see here is we have a foil, and onto this foil, we have exactly here in the center an inhomogeneity or a contamination, which is not clear, which could derive as a gel, air, or particle. So therefore, we need to check it. In this case, the example was too small to cut this in cross-section and analyze it in a cross-section manner. So therefore, it's really hard to say where it is located. So it's definitely not on top of the layers. So therefore, we could not wipe it away. So therefore, we delaminate, in this case, layer by layer in order to see where this contamination is being located. So what you see is that we have here this some bubbles around. So these are air bubbles caused by this particle here in the center. And this was then causing this delamination process. So what we did is we delaminate layer by layer in order to get access to this particle and analyze it with ATR. So then we just delaminated layer 1. We still see this bubble structure, so it's still hidden. So then we delaminate layer 2, and then we do not see this this bubble structure anymore. And now we see that we have clear access to the particle which is here in the center of this. So as mentioned, we measured this with ATR microscopy in this case. So we measured on and off this contamination, and what we know is there's a polyester layer present. So therefore, this is the polyester layer analyzed and displayed here in blue. And the particle itself in the center, this has been done and seen as calcium carbonate. So that means with this knowledge, we can now, the customer can now continue his evaluation. So where could this product during the manufacturing process being exposed by calcium carbonate in order to prevent this exposure once again and to improve the product quality. Another example of this of food packaging troubleshooting would, in this case, the homogeneity check of coated foils. So laminates get treated to increase certain properties to prepare next manufacturing processes. So, for example, to when other layers are attached to each other, or just if some printing of labels, brands, and design elements takes place, and therefore certain top layer must be clean or something like this. So in this case, we have here to check if a certain treatment or coating is homogeneous or not. Because with the homogeneity, also the quality is decreasing, for example. So that means we have here a PET top layer. This PET top layer is also coated with a polyester, and it should be homogeneously coated. Of course, we see also here this some in the visual some black structures, but usually these are being present on any sample, even if they are really homogeneous or not. So, but the visual inspection is not sufficient to answer the question if a coating is homogeneous or not. That means what we did here is an ATR imaging map across the foil's surface. And what we else did is then, with the result, a cluster analysis with 2 classes, which really reveals then the inhomogeneity. So we know that there is should be homogeneously the polyester being present. But what we see in these reddish flakes here, or in these reddish holes, I would say, is there we can see it's PET. So that means the structure or the coating is not homogeneous, and PET, so the hidden structure underneath the polyester, could be also being detected. And if we now overlay visual and IR information with each other, it exactly matches with these black spotted patterns in the visual, which is maybe some structural depressions on the sample where the coating has no access to, and therefore we have an inhomogeneous coating of the foil itself. Another example would be the characterization of multi-layer systems. In this, this is a very interesting topic because this is directly linked to reverse engineering of foreign packaging foils, which is also very interesting in order to see what is the competition doing with such polymer foils. So in this certain example, we have a foil which has a total thickness of 70 micrometers. And within this 70 micrometers, we have up to 8 layers. So that means, so we see a visual image, we see here our measurement area. So 8 layers within a 70 micrometer foil means that we need definitely a very high spatial resolution. And what we did here is in cross-section analysis, ATR imaging. ATR imaging with a field of view in this case of 120 by 40 microns. So this is exactly the area what we see here. And we have a pixel resolution of 1.25 microns. In other words, we have here the ability that each pixel sees an area of a sample of 1.25 micrometers dimension. That means we have a really accurate and high resolving measurement technique in order that we do not miss even the smallest layers in this case. What we else did is that we attached a PTFE buffer left on right side with the microvise holder like we did this before for our EVOH oxygen barrier analysis. And then we did the characterization of the layers. That means the characterization took place by univariate evaluation functions, and then each distribution we are assigning with this RGB imaging functionality a certain color code, and then we see the distribution of all components within one plot. And this is what we have done here. That means we see the spectrum here. We integrate, for example, the characteristic bands of a certain layer, and then we assigned it to a certain color code. And this is the way how we did it here. And this is how we can now see how PET, TPU, PA6, EVOH, or polypropylene are distributed. So we see that, for example, for PA6 and also polypropylene, these layers are present several times. So that means in order, in this case, with 8 layers hidden in structure. But this is also a very nice example to see how versatile this kind of technique is, ATR imaging or IR microscopy in general, that even the smallest layer, and even if the layer is from different polymeric identity, could be analyzed successfully with this technique. So I hope you see how versatile this technique is, in particular with the combination of FPA or ATR imaging in this case, and that we can even identify, distribute even the smallest structures with this product, and therefore IR microscopy is really a beneficial tool for troubleshooting in food packaging material. I hope you enjoyed our webinar so far. I would prepare myself right now for the question and answer session. So if you still have questions and you haven't asked them, please ask these kind of questions in the chat of here our GoToMeeting tool. And then after the small wrap up by Simon, I would be happy to answer your questions right away.